All right, we're at the last section of Chapter 2 for motion in two dimensions. We'll be looking at something called projectile motion, and we'll be looking at keywords like range, max height, time of flight, and this will be for objects moving in 2D. So let's get started. Okay, so projectile motion. So any object that moves in response to gravity along a two-dimensional curved trajectory is called projectile motion. Okay, so this means something is launched, kicked, thrown. Once it's in the air, there's no external engine or jets or helicopter blades or anything like that. It's just launched, and then the motion it follows is what we call projectile motion. Okay, with the only uh, force acting on it is gravity. Okay, so we have two objects here in this time-lapse photo, and they reveal some really interesting things. And I'll try and insert a little video here if I can get it to work. But if you have two rubber balls being dropped, the green one's being dropped straight down, the red one's given a little push, and it also drops. So when you look at the similarities and we look at the differences, obviously the red one moves away from where it started. Okay, in terms of a horizontal direction, it moves to the right. But if you look at the height, and this is the real important part, if you look at the height of all of those images between green and red, you'll see that they're the same. That means this object, okay, even though it's been pushed, the red ball has been pushed out of the little basket, it's still falling in the vertical direction exactly the same as the green ball. Okay, so when we think of this situation, in the vertical direction, that is the only direction where we have what we would call an unbalanced force. We have gravity acting in that direction. In the left and right direction, we don't have anything external involved in the problem. So that's what we're going to explore a bit, and is going to build our projectile motion discussion. So if we were to represent projectile motion with vectors, and this is where the vectors are really handy for seeing what's happening. So this is the same sort of idea, only something has been dropped out of a window and something has been thrown horizontally out of a window. So let's just look at the dropped object for a second. Let me grab a highlighter here. So this is just the straight dropped object right here. And you can see, because gravity, and we have acceleration due to gravity, that velocity vector is getting larger and larger and larger. So the longer it falls, the greater that velocity is going to be. If we look at the one that's been thrown out the window and has no vertical velocity whatsoever, so it's just the same as the dropped object, you can see from the vectors up here, okay, that it has a velocity vector to the right, and at each one of those locations, that little velocity vector to the right has not changed. That's because there's no external force, no external influence changing that velocity vector. So it's at a constant velocity to the right the entire time. But as the ball falls, just like the original ball or highlighter in green, it does have an element that's affected by gravity, and so it accelerates in that direction. And when you take those two components together, you get a resultant which gives you this path that the ball flies on. Okay, so the big takeaways from this are that two-dimensional motion, okay, is a combination of left to right motion and up and down motion. And we're going to build them together using our vector knowledge. Okay, the vertical motion is affected by gravity. The horizontal motion is not. Okay, so all our problems will disregard air resistance. If we included air resistance, then we'd have some factors affecting our left to right. But just for now, we're going to leave that out. So our only external influence is going to be gravity. Okay, so let's hide some of this because there's an awful lot of words. So in projectile motion, once the object is launched or projected, there is only one exterior acceleration taking place, and that is the acceleration due to gravity. We ignore air resistance at this point. So we just said that. Okay? So this means that the horizontal velocity never changes. Okay, while the vertical velocity experiences the effects of gravity similar to those one-dimensional problems in Chapter 1. So horizontal, because it never has an exterior or an external influence on it, and it will not have an acceleration in the horizontal direction, horizontal always is v equals d over t. But vertical, that will allow us to use our 5 kinematics because it does have acceleration due to gravity. That's big, so note that right there. Now when we go to talk about horizontal and vertical directions, there's lots of different notations we can use. Okay, keep an open mind. Different textbooks will use different things. Okay, so vertical notations, you'll see they use y's. We could use a v for vertical. I could be for initial, F for final. You could also have 1s and 2s in there. Horizontals might use X's or H. It's totally up to you. And a reminder, so our two-dimensional motion is made up of two one-dimensional elements, horizontal and vertical. Okay, and there's a really cool link here for PhET. And I'm going to try and bring it, but I know it's going to open it on my other window, so just give me a second to bring it over here. Okay, so let's see if we can fit most of that on the screen. Right there. Hey, that's what we need. Okay, so now, if we hit fire, boom, we launch the cannon and it fires. Okay, we can change the cannon and we can fire things. Okay, we can move the cannon up and down with different heights. Okay, you can change the speed that it's fired at. Bonk, hit that guy right down there. And perhaps the most important part, and this is the part we want to look at, okay, is you can turn on the vectors. So if you turn on your velocity vector, so I'm going to do this, I'm just going to slow this down a little bit, and I'm going to fire. Okay, and we can do that, maybe we can do that in slow motion. You can see that horizontal vector does not change. However, the vertical vector starts pointing upward. At the maximum height, it goes to 0, and then as it comes back down to Earth, it gets longer. Okay, so that shows you in a simulation how you can see how those velocity vectors are changing with different projectile motion. Okay, there are different ones you can model. So if we turn on, I'm going to turn off air resistance for now, and we'll turn on our velocity vectors, and we'll fire that. There's the resultant velocity vector. Let's turn it straight up, and we'll put on the components as well, and we'll go in slow motion. So you can see the vertical, at the very max, the vertical vector will go to 0 right there, and now it's on its way down, and that vertical velocity vector, oh, and I almost got the target, is changing. Okay, but the horizontal vector, one more time, watch the horizontal vector, it doesn't change. Okay, if we turn on the acceleration vector, you can see that it's constantly down, pointing towards Earth the entire time, which shouldn't be a big surprise because we talked about the acceleration on Earth is always down and towards the Earth. Okay, so we're going to do case 1 here. So case 1 is what we call horizontal launching from elevation. So when we look at this, we're going to break things up into two thinking or processes, vertical thinking and horizontal thinking. Okay, and that'll take a little while to get your head wrapped around. So we have a beanbag. It's thrown from a window 10 meters above the ground with an initial velocity of 3 meters per second. How long will it take the beanbag to reach the ground? That is, what is its time of flight? And how far will the beanbag travel horizontally? So what is its range? So if we look at the beanbag and we're thinking just in the vertical direction, what do we know that's given? Well, we know the acceleration is negative 9.8 meters per second squared. If the beanbag is thrown perfectly vertical, the initial velocity in the y direction is 0. Think about that for a minute. The component in the vertical direction is 0 if this object is thrown perfectly horizontal out the window. We know it's going to fall in a vertical direction down 10 meters. Okay, so now we need to use a kinematic equation because I have accelerated motion, and we want to figure out the flight time. So if we, start there, I'm going to choose kinematic equation number 3. And I'm choosing that, and it has the nice benefit of having the initial velocity goes to 0, so this gets really easy quickly. So now we have negative 10 meters, 0 here, 1/2, negative 9.8 t squared. Okay, so negative 10 equals negative 4.9 t squared. Divide both sides by negative 4.9 and then square root. So those cancel, and then we can square root both sides. And I'll need my calculator. Better scroll that up so we can see. So now we have 10 divided by 4.9 equals square root the answer, and we have 1.43. Okay, so the flight time is 1.43 seconds. Now, once we have the flight time and we know how long it's in the air, then we can come over to horizontal and list what we know for horizontal. We know the initial velocity in the x direction is 3 meters per second. We know that a is 0. There's no acceleration in that direction. So that means our equation is v equals d over t. So we know v, we're trying to find this dx, the distance or displacements in the x direction, so we need a t value, and that's where we can go back to the vertical knowledge and pull in the t value of 1.43 seconds. We put those together, 3 times 1.43 equals d, and we get about 4.3 meters as my displacement. And we didn't define a direction, so we could say to the right or out the window, to the right, and that would be the range. Okay, so I'm going to stop there. I will do case number 2 and number 3 probably separately, only because they take a little bit of time to navigate.